Okay, this is chapter 11, day 1. We are now in the chi-square distribution. Pretty cool. We're going to be doing our 5th and our 6th statistical tests, okay? Let's review them real quick. Don't write this down. Let's review them, all right? So we did a t-test, and that was for a mean, right? A single mean. And then we did a double mean test, okay? 2 means. And Texas Instruments calls that a 2-sample t-test. And those have intervals that go along with it, right? And if you recall, this was chapter 9 and this was chapter 10, right? Then we have a 1 proportion test, a single proportion, which is called a 1 prop Z on the calculator, the Texas Instrument calculator. And then we have a 2 proportion Z test, right? 2 prop Z. So when you start the process, when you see a bunch of data, and as you get toward the end of the course, you're going to ask yourself this question. First thing you do when you get data, you got to say, do I have a mean? Do I have a proportion? Or do I have a table? Okay. And if the answer is I have a table of some kind, and there's 2 different kinds of tables, then I'm going to do what's called a chi-square distribution. You may have seen this in AP Biology. They often do this in AP Bio. In fact, a couple of years on the AP Bio test, the chi-square distribution shows up. So the kids that have had AP Stats, are at an advantage. I always say statistics is the underpinnings of a lot of different disciplines as they go out to try to prove things or show their data. All right, so we're going to have 2 different kinds of chi-square distributions. One will be for a single row or column of data, and that's what we're going to do today in this lesson. And the other one is for multiple rows or columns, like a 2-way table that we saw very early in the book, okay? The single row or column is called a goodness of fit test, GOF, goodness of fit. And the reason it's called a goodness of fit test, and I got to move my face here so you can see that, goodness of fit, there we go, is because you're seeing how well or how good the data fits a preconceived notion. Okay, goodness of fit. Now, when we get into the 2-way tables in subsequent lessons, there's 2 different types, a test for independence and homogeneity, and we'll talk about that later. So today, it's a single row or column of values of categorical data, and it's called a goodness of fit test, okay? So let me erase the background of that, and you can kind of look here at what I'm writing. Single row or column of data. And by the way, this family of distribution is skewed to the right all the time. So, and I have it down here. The area is still 1, but it's not a normal curve. At degrees of freedom 1, it's check out my drawing there. It's super skewed. And then as you go up in degrees of freedom, it starts approaching a normal curve. It never quite gets there. I guess it would at some level. Okay. And you see all of that. So this is not a normal curve. Now, when we get to the requirements, remember the requirements in here are SPIN, the SPIN acronym. N is the one that keeps changing. For a mean, N stands for you need the number to be bigger than 30, or the box plot needs to show a normal curve, or the problem has to state we have normal data. For a proportion, you got to calculate 2 small equations. N times P has to be bigger than 10, and N times its complement, 1 minus P, or Q, has to be bigger than 10. For the chi-square, we have a little different interpretation of what N means in the number of samples, and we're going to get to that in a second, okay? All right, so let me slide down now. And again, as I always say, stop the video anytime you need, okay? Now, this is cool how we do this, okay? The chi-square. So this is really neat. Easy formula. O stands for observed. E stands for expected. And I'll explain what that means in a second. O minus E squared divided by E is going to show you how you calculate the chi-square distribution, okay? And there's a table for this, which I will show you as well. And you can use your calculator, okay? And degrees of freedom will be n minus 1, the number of cells. If you have 5 categories, minus 1, 4, okay? All right. So, by the way, on the calculator, this will be probably L1 minus L2 squared if you put it in a list divided by L2. Okay, and we're going to go over that as well. This takes some time. Okay, good. The mechanics of it when we get there will be pretty cool. Okay, the process of doing this. Okay, now for HO and HA, you do not have symbols. It's not like mu or pi. We just have words, okay? And you can write it many ways, but HO is something that means the same or equal. So I put the distribution of data turns out as you would expect, okay? And then HA, the distribution is not how you expected. Now, even though it is a not equal to thing here, when you shade it, it'll always be shaded on the right side. So even though it's a not equal to thing and you think in a two-sided test, no, the chi-square is always on one side. It's always on the right side. Okay? So here's your conditions and assumptions. And the S, P, and I are very similar. Here's the difference. You want at least 4/5 of the expected cells, the number, to be bigger than 5 of the expected cells. And the expected cells, you're going to figure out using common sense, and I'll show you how to do that, okay? And then you'll do some calculations, and there's lots of ways to calculate. You can do it by hand, you can do it on the calculator, and sometimes you can do it on Staplet possibly as well, okay? All right. And then there's all kinds of different things here that you can do. And I'm going to show you all of these. All right, so get that dialed in. All right, now let's go ahead and do one of these problems, shall we? Okay, so I got it in frame here. Let's say you have a die and you want to roll it. And you want to see if the die something's wrong with it. Maybe it's not balanced or whatever. So you roll it 120 times, let's say. So let's go ahead and write the numbers in here. Okay, so let's say I got 18 ones, I got 22 twos, I got 25 threes, I got 15 fours, I got 21 fives, and I got 19 sixes, okay? Now, if I rolled 120, this makes 120, by the way. If I rolled 120 times, how many would I expect? And the expected assumes HO is true. And HO in this case, HO will be the die is fair. Okay, the die works. Okay, HO, the die is fair. HA will be the die is not fair, it's unbalanced. So if you assume HO is true, then you're expecting 20 each. Now, expected doesn't mean it will happen. It means that would be the average. Great. Now, just looking at these, do those look vastly different? If you got 18 ones and 22 twos and 25 threes, etc., would you think something's wrong with the die? It doesn't look that off to me. But let's see how off it is, and we're going to turn it into a p-value. All right. So O minus E. So we got negative 2, right? This will be 2. This will be 5, negative 5. 1 1 and -1. Notice that O minus E balances out and makes 0. Now we're going to go O minus E squared divided by E, okay? Do this whole thing. Now, is there a quicker way? Of course there is. I'm going to show it to you in a minute, okay? So for right now, so let's see here. -2 squared is 4. 4 divided by 20 is 1/5. That's 0.2. So this is 0.2 and this is 0.2. Okay. And then we got 5 squared, which is 25, divided by expected, which is 20. 25 divided by 20 is 1.25, I believe, 1 1/4. And this will also be 1.25. Now, is there a faster way to do this? Of course, but let me finish it off. 1 squared is 1, okay? Divided by 20 is 1/20th, that's 0.05. And this will be 0.05. So if you look closely, these right here are all my chi-square terms, This is going to be the sum. I want the sum of all these. Okay. Now I'm going to show you how to do this a couple different ways. Okay. So we got to add all these up. Let me show you maybe a quicker way to do this. Okay. There's a couple ways, and this will be great. Okay. So let me flip over to the calculator at this time. All right. So I'm going to clear this. Okay. And you bring up the calculator. I think where to go. Coming in here. Okay, so here's the calculator. Got an inverse T in it. So I'm going to enter those numbers. What I did is I entered the observed in L1, and then I did in L2, I did the expected. And all I'm going to do on the L3, I got to be on the L3, not in the first cell, but on the L3, is I'm going to do observed, which is L1. So second in the 1 button, look at my parentheses I put. I'm going to subtract the expected, which is L2. Then I'm going to square it, which is right there, and I'm going to divide it by L2. O minus E squared divided by E. Okay? And those are those numbers that I did by hand. Okay? So you got to get these numbers added up for the chi-square sum. You got to get it added up somehow. Okay, so let's go ahead and add these up. Maybe I can use the software to do that. So I'm going to go second quit. I'm going to go stat calc 1 variable stats for L3, if you remember that. Okay, and there is the sum is I guess 3, correct? That's the E. This is the sum right here. Okay, so all those numbers added up to 3. Okay, sounds good. Add up to 3. All right, so let's go ahead and go back to the calculator now. I'm sorry. We'll go back to the distribution. So if you want to turn that into a p-value to see how rare that is to get a distribution of a rolls of a dice like that, we'll check it out. I don't think it's that uncommon. Okay. Obviously, if the chi-square term is 0, you have a perfect distribution. 3 isn't that big of a number, okay? So we're going to go second distribution, and I'm going to look for, where'd it go? Chi-square CDF, there it is. Looks like an X, but it's a chi-square CDF. All right, I'm going to type in 3. That's my chi-square sum, and I'm going to put some form of infinity in here. Now the degrees of freedom is 5. Now I know I rolled 120 times. It's not 119. It's the number of categories, which in this case is 6. The numbers 1 through 6. So 5, degrees of freedom 5. And I'm going to turn this into a p-value. Wow. Very, very common. It's basically 70%. There's a 70% chance I would get a roll of a dice like this if the dice was fair. So that's really common. There's nothing wrong with this dice. All right, now let's bring back up the notes here, okay? So what we got is the chi-square sum was 3. I added all those numbers, if you recall, okay? Then I'm going to type in chi-square CDF 3, comma, infinity, comma, 5, right? And I got basically 0.7000. There's a 70% chance we would get data like this, even if HO is true. So this is a failed to reject HO, failed to reject. There is not enough evidence to suggest that the die isn't fair. There's not enough evidence for that. This could have happened by chance very easily. And you could tell right away from the counts, okay? If I put the counts back up, right? 18, 22, 25. If you rolled the dice 120 times and you got this distribution when you're expecting 20 the whole time, you simply would not be surprised. That's not surprising at all. Okay. Let me show you another way to do this, and it's available on most calculators, and you might like this. Okay. Another way to do this on your calculator would be like this. I think most of them have this. Stat test, and Statlet may have it too if you look for us. Stat tests. And I'm going to go down to chi-square goodness of fit. There's 2 of them. Chi-square test is the one for tables with dimension, at least 2 by 2, but it's for 2-way tables. GOF, goodness of fit, is for 1 row or column of information. All right. So I typed in my observed in L1, my expected in L2, so I got it. And then I'm going to go ahead and draw this out. This will do it for you. Pretty cool, huh? That's really nice. So it adds up and gives you the chi-square sum all by itself here. It adds it all up right there. And then gives you that p-value of about 70%. Pretty cool. Very, very, very cool. Okay, the other way you can do this and get an approximate answer is you can go to your tables, and these tables are located on the internet, but obviously we have them for AP. And I mean, you got to locate the one. It's pretty obvious what it is. This is the one with the chi-square drawing on it. And so you'll get an approximate answer. You won't get an exact answer in most cases, okay? So you can look at degrees of freedom right here. Our degrees of freedom was 5, if you recall, 5, right? And our sum was 3, okay? Our sum was 3. Now, if you look at this, 3 is to the left of the biggest number, 6.63. So all we're going to learn is that the p-value is bigger than 25%. We won't know it's 70%. We'll know it's just bigger than 25. So this is okay to get an approximate. Now, let's say your chi-square sum was 13 for degrees of freedom 5. If that was the case, what you would do is you would look degrees of freedom 5, and you look for the closest number to 13, which is somewhere between here and here. You see that? Okay. And then look up and you'd realize, oh, the p-value is somewhere between 2.5% and 2%. And so you would write something like the p is between, 0.02 and 0.025. That's the common way to write it. You write it like that if you went to the table. Most of you will use software, but that is an option to get an approximate answer. Now, if you are off the chart this way, then your p-value is approaching 0. If you're off the chart that way with your chi-square term, okay? All right, let me clear that. Let's go on to the next problem. All right, there's one more here, which is kind of cool. All right, now class demographics at my high school. we're pretty sensitive to making sure that every student, regardless of ethnicity, gender, whatever, has an opportunity and is represented in the AP classes. So I often do an analysis of my classes, and I'm just picking one particular year. It's different every year, but one year I had 180 students, and I got the data here. Okay, so I had 180 students, and I put them in the 4 major categories that we have at our particular school. And I had 145 Asian students. That's a lot, but I'm also expecting a lot. I had 25 Hispanic students. I had I had 8 white students, and I had 2 students that were other, just didn't fit those 3 categories. Okay. How many am I expecting? Well, I'm not expecting 45 per category. No, you don't expect, I'm not expecting 45, 45, 45, 45 like dice, because that's not a uniform distribution. Dice is uniform. I'm expecting the same in each one. I'm expecting these percentages, because that is the school percentages of our community. Okay. So all that I did is multiplied 180 by 0.79, and I got 142.2. I know we can't have 0.2 of an ethnicity, but it is the expected count. Okay. And then if I multiply 15%, 0.15 times 180, I'm going to get 27. And then if I multiply 5% times 180, I get 9. And then if I multiply 1% times 180, I get 1.8. Okay. Now, again, just looking at this, just look at the numbers. I don't think my observed and my expected are that different. In fact, they're amazingly close. So I am very confident I'm going to get a high p-value, meaning this would be very common if HO is true. Okay. So no big deal at all. All right. Now, in writing this up, how would I write it up? No problem. Okay. So HO would be, right? Stats represents the school, right? Demographically. I'd write more than that, but I'm running out of room here. HA would be, I'm going to do it really quick. It's not representative, right? Does that make sense to you? Because it would be very different. Not representative. Okay, fine. Okay. Now, I am not going to do this O minus E squared divided by E by hand. I'm not going to do that. That's a little too crazy for me. So I'm going to go ahead and type it in my calculator and do this 3 different ways. Okay. So let me clear this and go to my calculator, and I have it pre-slugged in. What I did is I put it in L4 and L5 prior to the lesson here. All right. So there, in L4, there's my counts. All right. My degrees of freedom will be 3. All right. And there's my expected. Now, remember, I want 80% of my expected values bigger than 5. I only have 3 of the 4 expecteds bigger than 5. I'm a little light on numbers, but I have a census because I have all 180 kids. So I'm not really worried about that, but watch for that. You want all the cells to be bigger than 5, but if all the expecteds, but if one of them isn't, you still want 80% of the expecteds bigger than 5. I don't quite meet that parameter, but that's okay. I'm just going to keep going with the test. All right. So what I'm going to do is I'm going to go over to L6. I'm going to calculate this. I'm going to go, let's see here, parentheses, observed, which is L4, O, minus expected, which is L5, squared, divided by L5. All right, O minus C squared divided by E. All right, there we go. Now, looking at this, sometimes I'll ask you which category contributes the most to the chi-square term. The second category is the biggest chi-square term. It's not very big. None of these are big at all. But that second category contributes the most, okay? And that would be the, I think that's the Hispanic category, is the biggest contributor to the chi-square sum, although it's not that big of a deal. Sometimes you'll have a huge number in one of the categories and you kind of know which one's off. It's also really evident to the naked eye, but it's neat to put it into stats words. All right, so I need to add these up. The fastest way to do that is just to use my calculator and go stat, let's see your second quit, stat calc, one variable stats for L, well, I think it's L6 in this case, right? L6. Okay. And I got, let's see, the sum is really small, 0.3366. 0.3366. I'm going to memorize that. 0.3366. I'm going to make it into a p-value. Second distribution chi-squared CDF. Put in my chi-square term, 0.3366. Some form of infinity. My degrees of freedom is 3 in this case because I had 4 categories of data and I subtracted 1. Okay. Oh, wow, this would happen, something this unusual would happen 95% of the time. It makes sense. I almost have a perfect distribution. What I was hoping to get in terms of ethnicity to represent the school in my class, I got. So it's almost a perfect representation. So 0.9530, fantastic, okay? Now, is there a quicker way to do this? Of course there is, all right? So you could go stat, tests, and most calculators have the goodness of fit tests. So go GOF, and then I got to go L4 was observed and L5 was expected. My degrees of freedom was 3. Okay. Look at that. Pretty cool, huh? So nice. There it is. There's a 95% chance I would get this data by chance, even if HO is true. So we have a fail to reject all the way. All right, great. Okay, so let me lower this here. So if you're doing this, if you were to draw this out, this was like 0.95. This is 0.3366, something like that. So you draw it out, shade a huge amount of it. Okay. All right. And I asked some of these other baby questions down there, but that's a fail to reject, all right? So there you go. That's an introduction to the chi-square distribution. This is the 5th of our 7 tests we're going to run. This is the 5th one, right? The first 4 were using means and proportions, and this one is counts in a table, all right? So that's the chi-square distribution. Day 1 of just 6 days on this lesson for chapter 11. Thanks a lot.